Guys, again, let me just go over the calendar, give you an idea of what to expect this week. So we're gonna do optimization today. There will be one optimization problem on the quiz. I'll tell you exactly what it's going to look like, and it'll show up on your quiz review packet that you picked up today. Tomorrow we'll do quiz review. Wednesday we'll do quiz review. Thursday I'm going to start 6.1, but if we get done with that topic, we can do a little bit of quiz review on Thursday, and then Friday quiz review at the end of class, because I need to cover 6.2. The hope is that I can cover 6.1, 6.2 Thursday and Friday. I don't lose any days of instruction, but I also give you an extra day, extra couple days over the weekend to study for your quiz. Your quiz will be next Monday, okay, right before the PSAT day. Okay. Help sessions. I'm doing help sessions early this week for my AP students. They have an upcoming quiz on Wednesday, so I'll do help sessions for you guys Thursday morning, Friday morning, and Monday morning. Okay. Yes.
What's going on SAT day on the 9th? Is that virtual or?
No, well, SAT day is only for students, seniors who signed up to take SAT, so it won't affect most of us. It'll still be a regular school day for most of us. Yeah, so it's just a normal day, but yeah. PSAT, it is. There is no afternoon schedule, so it's basically, once PSAT is done, then everyone goes home. There's no. In the past, they would have like an afternoon reduced schedule, but there's none of that. Once PSAT is done, the school day is over for any students who are here. Yeah.
So if you're a senior, can you just not show up and not say or do anything, and it'll not?
I have to figure that. I think. Yeah, I think seniors are just going to be staying home. It's just the 9th through 11th graders who need to be here on that day. Yeah. Yeah. Okay. Any questions with our calendar here? All right. Let's go to page 43. Our optimization notes. Okay, so optimization is the process of finding the greatest, which is the maximum optimal solution, or the least value of a function, the minimum optimal solution for some constraint, which must be true regardless of the solution. Optimization finds the most suitable value for a function within a given domain. It sounds complicated, and the reason that it feels more complicated is because it's in a word problem kind of format. And there's potentially two variables involved that we have to get it down to one variable. But the big picture is, if I can get my equation down to one variable, find the derivative, find a critical point by setting my derivative equal to 0, then that's basically where my answer point is going to be. Wherever my slope is 0 is going to be where my optimal solution is going to be. And there is no separate process between maximum and minimal optimal solution. Just think, okay, whatever causes my slope to be 0, that's my optimal solution, and that'll be where my answer is. Okay, or my answer is circling around that value. After that, I just have to plug into my original equation and find whatever the problem is asking for me to find. Okay, so we're going to write the equation for the variable that you want to optimize. We're going to substitute to get the equation in terms of one variable. Usually, we need a second helping equation to get our main equation down to one variable. Once it's down to one variable, we just find the derivative, set the derivative equal to 0, and then solve. Okay. And similar to related rates in the sense that they have a word problem format, and also the calculus is not the difficult part. A lot of times the calculus is just power rule. It's the setup that's a little bit different. Okay. All right, so example 1. Manufacturer wants to design an open box to have a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So we have these constraints
It's got to be a square base. Surface area has to be 180 square inches. And it's an open box, meaning that there is no top. It's just 5 sides. And using those constraints, how can we build the box with the largest volume? Okay, so let me list out some information here. Surface area is 108 square inches. And we have two formulas that we're going to be working with. Here, the dimensions are length is x, width is x, and height is h. And if we want to build our volume formula is just length times width times height, which is x squared times h. Now, surface area, you're going to have to build your own surface area formula, okay? So this will not be given to you. But surface area is just area of each of the surfaces, okay? How many surfaces are we having in this problem? 5, right? So let's build one area at a time. Let's start with the base. What's the area of that surface? Just x squared, okay. Let's do one vertical face here. What's the area of the one vertical face? XH, okay. And then how many vertical faces do I have? 4. So every surface has an area associated with it. My base is x squared, and then each of the vertical sides is xh, combined like terms. My surface area is just x squared plus 4xh. Okay. All right, what dimensions will produce a box with maximum volume? So anytime you see the word maximum or minimum, look at to see what it's describing. Whatever it's describing is what you want to find the derivative for. Okay. So this is our main equation. We're trying to find the derivative. It's going to be v prime of x. It's not dv over dt. Time is no longer the independent variable. We're going back to x being the independent variable. So it's basically have to find v prime. But we want to get this down to one variable here. And we're going to try to decide which is the easier variable to do. But we're going to keep working on this here. Surface area is x squared plus 4xh. We do have a constraint, 108 square inches. I'm going to plug 108 in for s because we do have that value. So now we're down to 2 equations that we want to work with. It doesn't matter which variable that we solve for, but we want to solve for the variable that is potentially easier to replace. Let me see for this one. Okay, I think this one I'm just going to solve for h here. Even though there may be some fractional values, I'm just going to, but technically you can solve for both either variables, assuming that both are possible to do. I'm going to just go ahead and just get my volume equation down to one variable in terms of x. So I'm going to solve for h. Oh, sorry, for xh. Thank you. That's where. Okay, so that's why we're going to solve for h. Because that's the easier variable to isolate since there are 2 x's here. So I'm going to eventually work my way down to solving for h. Okay, so there's my h equation. This is my substitution into my volume equation. My ultimate goal is get my volume equation down to one variable on the right side. Then I can clean it up, go through power rule, find the derivative, set equal to 0, and then whatever critical point I can find is going to be where my solution is going to be circling around. Okay, so my h is just 108 minus x squared over 4x. Okay, no need for any complicated rules. All we need is power rule. Notice that this is a fraction, but there's only one term in the denominator here. We can just split everything up into individual fractions and just take care of them individually, and just all we need is power rule. (108) and 4 can reduce to be 27. Can pull the 1/4 out. Now it should be a relatively easy derivative process here, just power rule. V prime set V prime equal to 0. So whatever causes my rate of change of volume to be 0 is where that optimal solution is going to be living in. So just solve for x. I get 3/4 x squared equals 27. Divide both sides by 3/4, which is the same thing as multiplying by 4/3. I get x squared equals 36, which means x has to be 6. We're talking about a positive length. So technically, algebraically, we get plus or minus 6, but only 6 makes sense for our problem. So we know that our optimal solution is going to exist when the base are both 6. And so if I want to find the dimension, I just have to find my h. And because I have h defined from a previous setup, I can just plug x6 in for my x and then solve for h. My h is 3. So sometimes it's asking you for the optimal volume. Sometimes it's asking you for the optimal dimension. So after you find your solution, you just have to read the problem again and make sure that you're providing the data that they're asking for. So they're asking for what dimensions will produce a box with a maximum volume. They care about the dimensions here. So 6 inches by 6 inches by 3 inches. Okay, next page, page 44. Rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular regions. What dimensions should be used so that the enclosed area will be a maximum? So this is the hint, right? We're trying to maximize area. And we have 200 feet of fencing. So this is related to perimeter. We're basically working with perimeter and area. The perimeter will be the help equation to try to get the area equation down to one variable. Once we get our area equation down to one variable, we just clean it up, find the derivative, find the critical point, and our solution will be there. So let me draw the region here again. Okay, this is what we know here. Perimeter, we have 200 feet of fencing to work with. We're trying to optimize that amount of fencing into the largest area possible, but it's got to be 2 rectangular subdivided regions. So area, put a star next to this because this is ultimately our goal to try to find the derivative. But let's build the area first. What's the area of this region here? Yeah, length times width, right? 2x times y. Okay, the perimeter in terms of the variables here. Okay, So we know perimeter, we have 200 feet to work with. We typically want to try to find the easier variable to replace, but this one, it's going to be the same. We're going to be left with fractions either way. I'm going to solve for y just because I like my, if possible, I like my equation in terms of x. That's just a preference, but it doesn't really matter. But let's go ahead and solve for y. If you want to solve for x, you can. I'm going to solve for y so I can replace y in terms of x. So let's just try that. Once you get this in terms of y, you can make that substitution. And then once you get your area equation down to one variable, then clean it up. The only thing you need is power rule. We shouldn't have to deal with anything more complicated than power rule. So try that. See if you can solve for y, make that substitution, get your area equation ready for power rule, find the derivative, solve for x, and then look for your dimensions. So my area equation is, after I clean it up, it's just 400 over 3x minus 8 thirds x squared. We find the derivative, set equal to 0, solve for x. Once we solve for x, we look at what the problem is asking. If they're asking what is the maximum area, then you just have to find out what the area at that x value is. If they're asking for dimensions, then we need the width as well. So plug x into one of the equations where you can solve for y. The y is 100 over 3. So the dimensions, you can either say that the dimensions for x, which is 25 feet, or if you want to say the dimension of the full width of the fencing, it'll be 50 feet, but either way is fine. 50 feet by 100 over 3 or 25 by 100 over 3 feet. Okay, page 45. Let's talk about some problems where we're going to be optimizing cost. Or minimizing cost. Okay. I'll use a separate sheet just so I have enough space. I don't know if I gave you enough space for number one, but should be okay. All right, rectangular field is fenced off along the bank of a river. So we have river on one side, and then we have a rectangular fence. So no fencing along the side where the river is. The material for the fence costs $8 per running foot for the two ends, and $12 on the side parallel to the river. Find the dimensions of the field of largest possible area that could be enclosed with $3,600 worth of fence. So largest possible area, we know that we're trying to optimize area, and then $3,600 worth of fence. This is going to be associated with your perimeter. So your cost is going to be built into your perimeter equation. Okay, I'm going to use X for my horizontal and Y for my vertical component here. And there's different material for the two sides here. So the one that is the two ends is going to be the cheaper material. So $8 per foot. But then the one that is parallel is going to be a little bit more expensive, $12. Okay, so let's build the area. The area is not going to have any cost associated with it, okay? Because we're not paying for what's inside here. We're paying for the perimeter, the fencing. So what's the area?
XY.
Just XY, yeah. And the cost is going to be merging the perimeter and the price together. So the cost will be, if I just multiply and add all this together, 12x plus what? 16y. And how much money are we trying to use up? 3,600. Yeah. So this is the equation we're going to be working with. Okay. So we can either solve. We know we're trying to optimize area, so we're trying to get our area equation down to one variable. In this case, it looks like both variables would be equally similar difficulty, but I'm just going to solve for y if we just want to be on the same page. But if you solve for x, that's fine. But let's see if we can solve for y. Get our equation down to x. The only thing we need is power rule. So spend your time cleaning up your area equation, find the derivative, solve for x, and then you can come back and read the problem again and see what are they asking for. Are they asking for the dimensions? Are they asking for the minimum costs? Are they asking for the area? Okay. Again, derivatives should be the easiest part of this process. We shouldn't have to deal with any messy derivative rule. You only have to deal with power rule. So spend the time to clean it up so you're dealing with a relatively simple derivative process. Okay, I solve for y here. Y is equal to 3600 minus 12x all over 16. Plug that into my area equation because I'm trying to optimize area. I'm trying to find the derivative for area, but I need area down to one variable. So I try to get in terms of x. Once it's in terms of x, clean everything up. No need for quotient, chain, product rule. The only thing we need is power rule. So split up all your fractions so you get a nice clean condition for power rule. Then find a prime. Set a prime equal to 0. Solve for x. Once you solve for x, you know your answer is circling around that 150. And then read the problem again. Looks like they're asking for dimensions. So all you need is y. So find the equation for y, plug that in. So once you solve for x, you're just searching for what to plug in, right? There's no more new equations you're trying to create. You're just looking back at what you've already created and just finding the value that you need. Okay, any questions with 1? Okay, let's try number 2. Yes.
For my x, I found negative 150. So like if you get a negative number.
Yeah, let's look at. I think look at your signs again. We should always get a positive value. So look at something may have gotten add or subtracted incorrectly, but yeah, we should always get a positive number. We shouldn't have to flip the signs. We should get the positive in return. Okay, I'll look at your work too at the end if you're still having.
Oh, I think I figured out why. Got it. Okay. Yeah.
Okay, let's look at number 2. Any questions with 1?
Because I said it equals 0 instead of 3,600.
Got it. Okay. All right, so let me read this problem here. We have a rectangular storage container with an open top to have a volume of 10 cubic meters. The length of its base, sorry, I meant to say length of its base is twice its width. Material for the base costs $10 per square meters. Material for the sides costs $6 per square meters. Find the cost of material for the cheapest container. We're trying to optimize surface area. All right, so let's build our, let's identify some variables here. I know that my length is twice its width. So I'm going to call this side my width and my length is twice the length of it. So I can use the same variable because I have a direct relationship between the length and the width, but they don't give me any relationship between the height and the width. So I need to use a different variable there. I will use h. You can use y as well. It's up to you. I'll use h for height. Okay, so let's do volume first. That's the easier equation, right? What's the volume formula for my box here? Yeah, so length times width times height. So 2x squared h. Now they do give us a volume to work with. So we know 10 is equal to 2x squared h. We'll come back to that. We're trying to find the cost of material for the cheapest container. We know that we're trying to optimize the amount of material that we're using, and that's related to surface area. So let's build our surface area. And then we can factor in the cost as well. Okay, surface area. How many sides are we dealing with here? Good, because why?
It's open top.
Open top, yeah. So if it's closed top, then we will have a material at the top, but if it's open, only 5 sides. Okay, let's deal with the base first. Okay, what's the area of the base? 2x squared, okay. What about the front-facing vertical side here? What's the area for that? This side here, 2xh, okay. You don't have to do it, you don't have to do it in the order that I'm showing, so you want to kind of be consistent for now. And then there's also a back face, right? that's also what? 2xh. Good. Okay. What about the side vertical side here? xh, okay. And there's two of them, right? So if we count, we should have five area surfaces, right? So we have the base, two front facing longer size, bigger size, area size, and then we have the two smaller size. So 1, 2, 3, 4, 5. Okay. The sides are all the same cost. It's $6 per square meters, but the base is the more expensive one, is $10 per square meter. So I'm gonna do 2x squared plus this is 6xh. The cost associated with the base is $10. And the cost associated with the size is $6. So all I need to do is to multiply that through, and that will be my cost equation. Any questions up to this point? Okay, so now we're trying to optimize cost, which means I'm trying to get my cost equation down to one variable. And this one, we see that the easier variable to solve for is h, right? It's going to be tough to solve for x because you got x squared and x here. There's only one h here. So I'm going to find a replacement for h. And this is where my volume is going to come and help me out here. So if I solve for h here, I can plug that. Sorry, the arrow should go the other way here, this way. So if I solve for h equals 10 over 2x squared, which is the same thing as h is equal to 5 over x squared. So this is what I'm plugging in for h. Okay. My goal is to get my optimizing equation down to one variable. H is the easier variable to replace. So then once I make that substitution, clean up my cost equation, get it ready for power rule, find the derivative, find a critical point, and then my answer is going to be circling around that number. Five over x squared, not just 5x for h. Because if I'm dividing by 2x squared, I can reduce to 10 and 2, but the x squared can't move up. It needs to stay in the denominator. Okay, once I get my cost equation down to one variable, I'm ready to find the derivative and set equal to 0. Once you solve for X, you go back and read the problem. It says find the cost of the cheapest container. So we just have to find a cost equation to plug 1.65 into. Make sure you plug into one of the cost equations and not a C prime. Okay, your homework is directly in your packets, page 47. I copy and pasted the homework directly onto your packet. And then AP practice as well, page 49 to 50. So basically, page 47 to 50 will be your homework for tonight. Okay. And I gave you the quiz review packet. We didn't get a chance to get to it, but tomorrow and Wednesday, we'll have full class periods to do our quiz review packet. Okay, all right, come get your phone. On this. He's stretching my thumb.